I call upon Professor Dr. Bandit Apon, the President of Chulalongkorn University, to present his welcome remarks.
Your Excellency, the ambassadors to Thailand, Professor Takaaki Kajita, Nobel Laureates for Physics 2015, Mr. Uwe Morawetz, Chairman of the International Peace Foundation, distinguished guests, students, ladies and gentlemen. It gives me a great pleasure to warmly welcome you all to Chulalongkorn University to attend the prestigious JAPAN-ASEAN BRIDGES event series, jointly organized by Chulalongkorn University and the Institute of Peace Foundation. Our collaboration dates back to the event series entitled Bridges, Dialogues Towards a Culture of Peace, initiated by Mr. Uwe Morawetz as an independent contribution to the United Nations Decade for a Culture of Peace and Nonviolence that took place from 2003 to 2005. After the resounding success of that series that brought together several Nobel laureates, other keynote speakers and artists who all reached out to a vast audience of over 200,000 across the Southeast Asian region, Bridges has now returned to Thailand with the renewed aim of bridging together the best and brightest minds of the world from November 2023 to March 2024, Nobel laureates in physics, economics, and medicine. This illustrates gathering will certainly inspire and stimulate academic exchange and enhance further development in several key areas through education. We are particularly proud to be co-hosting this event, which commences today with a keynote speech by Professor Dr. Takaaki Kajita on a most pertinent topic entitled The Importance of Science for Peace Building, following by a speech talk from Dr. Chananit Asawatangtrakundi, our instructor from the Faculty of Science, to share her invaluable insights and experiences. May I also take this opportunity to convey our thanks to our esteemed business sponsors, comprising BMW Thailand, Dusitani Hotel and Resorts, Kasikorn Bank, and Mitsui Fudosan Company Limited. Thank you very much.
Thank you, Mr. President. And now may I invite Mr. Uwe Morawetz, the Chairman of the International Peace Foundation, to deliver the opening remarks.
Sawadee krab, sabadiไหมครับ? Welcome to the Japan-ASEAN Bridges event series facilitated by the Vienna-based International Peace Foundation. The events are hosted in cooperation with various local partners, including some of the country's main universities, and I would like to thank Chulalongkorn University for hosting our event today. Commemorating the 50th anniversary of official relations between Japan and the ASEAN region, Bridges will be continuously held in Thailand and Japan until March, involving the participation of Nobel Laureates for Physics, Chemistry, Medicine, and Economics. The Japan-ASEAN Bridges series follows the series of over 800 Bridges events which the International Peace Foundation has facilitated since 2003 to support education in the ASEAN region. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and interdisciplinary approach towards peace. The foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where representatives of science, politics, economy, culture, religion, the media, and youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. Therefore, the foundation itself is a bridge and a facilitator between different language groups in our divided societies, where politicians speak another language than scientists, and business and artists speak another language than business leaders and political leaders. In a highly interdependent world, problems cannot be solved by only one of these language groups only, but by working together. The aim of Bridges is therefore to facilitate and strengthen dialogue and communication between societies in Asia with their multiple cultures and faiths, as well as with peoples in other parts of the world, to promote understanding and trust. The events aim at building bridges with local universities in Asia to establish long-term relationships with Nobel laureates in all fields, which result in common research programs and other forms of collaboration. By enhancing science, technology, and education as a basis for peace and development, the events may lead to a better cooperation for the advancement of peace, freedom, and security in the region, with the active involvement of the young generation, our key to the future. This is why Bridges is not designed as a one-time event, but as a continuing process of synergies of now over 2 decades to make the series of events a sustainable success for Thailand and for Asia as a whole. I am grateful to our honorary chairman, Anand Painirachun, and to our partners and sponsors who have enabled us to make Bridges a reality. I would like to thank everyone present today for taking part in this program. May it help us to facilitate a new culture of peace through dialogue, transcending its definition as merely the absence of war or armed conflict into a new understanding of what the basis for peace is: education. In this spirit, we welcome today the 2015 Nobel Laureate for Physics, Professor Takaaki Kajita, who has agreed to come to Thailand to support the events. And we all look forward to his keynote speech and to his important contribution towards peace. ขอบคุณครับ
Thank you, Mr. Morawetz. Please kindly remain on the stage, and may I request that you to be joined by the President of Chulalongkorn University, Professor Dr. Takaaki Kajita, Professor Dr. Pranat Pothiyarat, and Dr. Shayanit Asawat Tangtrakundi for group photo session, please. And thank you. May I request Professor Kajita to remain on the stage? With the event now officially declared open, we shall proceed with the keynote speech by Professor Kajita, who is a recipient of the Nobel Prize in Physics for 2015 in recognition of his contributions to the experiments which demonstrate that neutrinos change identities. This metamorphosis requires that neutrinos have mass. The discovery has changed our understanding of the innermost working of matter and proved crucial to our view of the universe. Ladies and gentlemen, please welcome Professor Dr. Takaaki Kajita.
Well, first of all, thank you very much for the kind invitation to the Chulalongkorn University for Japan-ASEAN Bridge event series. It is really great honor for me to speak in this auditorium. Today, I want to talk about the importance of science for peace building. Based on my scientific experience on neutrinos and gravitational waves. This is the outline of this talk. First, I'd like to briefly introduce you about my research location. Then I want to move on to neutrino studies, gravitational waves, and I want to summarize this talk. First, let me introduce where I'm working. Well, you see the map of Japan, and our experiments are located there in the mountain area. In fact, please look at the right panel. This shows the inside of a mountain where we have the super Kamiokande neutrino experiment. In addition, we have the Kagura laser interferometer to observe gravitational waves. So I have been working on these experiments. So today, I'm going to talk about our collaborative work in Super Kamiokande and Kagura. Okay, first, I'm going to talk about neutrinos. And probably some of you have no idea about neutrinos. So let me briefly introduce what are neutrinos. Neutrinos are fundamental particles like electrons and quarks. They are very small particles. And if I'm asked to tell a little bit more about neutrinos, then I want to say that neutrinos are something like electrons, but without electric charge. In fact, this has a significant consequence. Neutrinos can easily pass through even the Earth or even the Sun. And neutrinos have three types, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to mention that neutrinos have been assumed to have no mass. Now, how can we study neutrinos? Well, here in this cartoon, I want to show you the idea. Well, neutrinos can easily pass through even the Earth, but sometimes a neutrino can interact with a nucleus in an atom. Then, typically, a charged particle is created. Actually, we have many ways to observe these charged particles. For example, if the nucleus is a water nucleus, then this charged particle propagate in water. Then, while propagating in the water, this particle emit Cherenkov photons, or simply photons. Then we have various ways to detect photons, I mean light. We can easily observe light. So we use photodetectors to observe these photons, and by analyzing the photodetector data, we know the details of the neutrino interaction. So this way, we study neutrinos. Now, the detector is Super Kamiokande. It is a very large neutrino detector. It has about 40 meters in diameter and 40 meters in height. And it is located about 1 kilometer from the top of the mountain, very deep underground. And indeed, the detector is very big, as you can see by this photo. This is the inside of the Super Kamiokande detector. And this photo was taken when we constructed the Super Kamiokande detector in 1996. Now, I'd like to show you this photo. This photo was taken at the Institute for Cosmic Research, our institute, in 1992, when we first discussed the US-Japan collaboration in Super Kamiokande. Well, the meeting went well, and we agreed to work together. And around that time, we had about, say, 100 people in Super Kamiokande. And, and we, of course, we worked together. For example, this photo was taken in the spring of 1995 when we constructed the Super Kamiokande detector. And indeed, we worked together in underground for about a year to construct the detector. And in my opinion, these works were extremely important to understand each other, who have different cultural and historical background. So, in my opinion, after these very difficult construction work, we really understood each other and we really collaborate. Now, in Super Kamiokande, we study neutrinos. And here in this talk, I just want to mention one neutrino source. Neutrinos are created in various ways. But here, I'd like to focus on neutrinos created in the atmosphere of the Earth. Well, cosmic ray particles, they are high-energy particles coming from the universe somewhere to the Earth. And these particles, once come into the atmosphere, they interact with air nucleus, typically producing pions. But pions are unstable. They decay to other particles, and during this decay chain, neutrinos are created. And of course, these neutrinos, almost all of them, pass through the Earth. But some of them interact in the Super Kamiokande detector. why we study these neutrinos? Well, when we started the Super Kamiokande experiment, there was some hint that neutrinos oscillate, well, or neutrino oscillations. And I want to briefly explain what are neutrino oscillations. If neutrinos have small mass, neutrinos change their type from one type to the other. For example, as shown in this slide, if a muon neutrino is created in the left corner and begin to propagate to the right, then at some point, the neutrino type changed to tau neutrino, but this neutrino continue to propagate, then the neutrino type come back to muon neutrino, then tau neutrino, and so on. So people predicted that if neutrinos have small mass, neutrinos change their type. So this is neutrino oscillations. And we wanted to study if this is occurring in the atmospheric neutrinos. So from the beginning of the experiment, we carefully analyzed these data as a team of 100 people. And in 2 years, we were able to show evidence that neutrinos indeed oscillate. Well, maybe this is not a place to discuss the detail of this graph, but still, let me explain. Well, here, the horizontal axis shows the neutrino arrival direction. One means downgoing neutrinos coming from the above atmosphere, and the -1 means neutrinos coming from the other side of the Earth, upward-going neutrinos. And the vertical axis is the number of neutrino events. Then, by the way, the black circles data and the hatched histograms show the simulation results. And then you find for downgoing neutrinos, the data and simulation agreed well. However, for the upward-going neutrinos, the data showed almost a factor of 2 deficit compared with the simulation. And this can be easily explained by assuming neutrino oscillations, namely neutrinos created in the other side of the Earth propagate in the Earth, then the neutrino type changes while propagating, and therefore, when they arrived at the Super Kamiokande detector, only half of the neutrinos are muon neutrinos. So this was the discovery of neutrino oscillations. And indeed, we were very happy. This photo was taken in 1999 at the top of the Super Kamiokande detector, when we heard the news that Super Kamiokande collaboration will be awarded the Asahi Prize. This is a very prestigious prize in Japan. Well, at the time, we were a team of slightly more than 100 people from 4 countries. But anyway, after that, people realized the importance of neutrino physics, and therefore now Super Kamiokande collaboration has about 230 people from 11 countries. So, well, this collaborative work was really very important to produce scientific results promptly. Well, physicists were really excited with the discovery of small neutrino mass. But you may ask, why you are so excited? Why neutrino mass are so important? Well, we think, indeed, neutrino mass are very important. And please give me 30 minutes to explain, 30 seconds to explain why. Well, here, the horizontal axis is the mass of a particle. And red, green, and blue colors show fundamental particles. And, well, so these fundamental the mass of these fundamental particles are known. Now, it is about 25 years we begin to know the neutrino mass. And during these 25 years, we understood the neutrino mass very, very well. Well, actually, not perfectly well, but still, our knowledge on neutrino mass is advanced. Therefore, let me plot the neutrino mass here. Then the neutrino mass is there. Then you find that the neutrino mass is plotted in a very different place in this figure. Then you immediately notice the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. 10 orders of magnitude smaller. Very small. Because of this extremely small neutrino mass, we are excited and we believe this is the key to better understand elementary particles and the universe. Now, in fact, we think neutrino mass are really important to understand even the fundamental questions in the universe. Here, I show a photo of the far universe. There are many galaxies. And there's one thing we know. All of these galaxies are made of matter particles. There's no antimatter galaxy. Well, this is kind of trivial. However, if we think about the Big Bang universe, this present-day universe cannot be easily understood because at the Big Bang universe, the universe was extremely hot, and therefore we expect there have been essentially equal number of particles and antiparticles. Then with the universe cooled down, particles and antiparticles meet and annihilate, disappear. Therefore, we naively expect there should be nothing left in the present-day universe. But of course, we know particles remains. This is in fact a mystery. But there's an idea that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So we are excited, and therefore we'd like to attack this question with a very big neutrino project. Well, this is a newly planned experiment, which is under construction. This is called Hyperkamiokande. It is going to be a very, very large neutrino detector. And I want to say, this is really a very large detector and therefore very large collaboration. We have about 600 members from 22 countries. And let me show you about the Hyperkamiokande collaboration. I'm sorry, this is a slightly old slide, but anyway, in Hyperkamiokande, we have collaborators from almost all over the world. And in particular, I want to mention that there are collaborators from Ukraine and Russia. So, well, certainly, if the world is peace, if there's no war, we would like to work together. Unfortunately, well, of course, we still want to work together, but the situation is very complicated now. But our hope is we really work together in the Super Kamiokande collaboration. And this way, I hope our colleagues in Ukraine and Russia will be happy. Now, I would like to move on to the second topic, that is the gravitational waves. Well, gravitational wave was predicted by Albert Einstein slightly more than 100 years ago. Well, let me explain what is expected based on the simulation. Here in this movie, you see two black dots. They are black holes orbiting each other. And during this orbiting, they emit gravitational waves. And therefore, with the time, they come closer, 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 and orbiting faster and faster. So they came very close, and movie slow down. And finally, these two black holes merge, and a heavier black hole was formed. Now, if you look at the outside space, you find that gravitational waves are propagating outside. So this is the gravitational wave. We'd like to observe this wave, and through the observation of this wave, we'd like to understand the black holes or some other heavy and compact objects in the universe. Then the next question is, how can we observe these gravitational waves? And to observe these waves, we use laser interferometer technique. So this way, this is the laser, and the beam is split into two, and then the beam is reflected by the mirror at the far side, and then come back and interference here. And typically, the interference light is minimum in the screen. However, by some reason, if the mirror position changes, the interference pattern changes, and this way, we want to observe gravitational waves. So if we observe this kind of the intensity change in the interference light, this could be the evidence for the gravitational waves. And indeed, in September 2015, this kind of signal was observed by 2 LIGO laser interferometers in the United States. And you find, by the way, the graph shows the curve shown by blue and orange, and they are 2 independent data from 2 independent laser interferometers. And you find these 2 data agreed quite well. And from this data, we understood that 2 black holes of 36 solar mass and 29 solar mass each merged at the distance of 1.3 billion light years, newly forming a 62 solar mass black hole. And we believe this was really a great discovery. Gravitational wave astronomy was born. And since then, people are continuously observing gravitational waves. And this is a summary of the events so far observed. A total of 90 events were so far observed. And really, we begin to understand black holes from these observations. So, we'd like to contribute to this exciting field. And therefore, we have been working hard to observe gravitational waves in our collaboration. This collaboration is called Kagura collaboration. This is again an international collaboration. We have about 150 people seriously involved in this collaboration from 8 countries and regions. And you see that Kagura collaboration is essentially an Asian collaboration. China, Hong Kong, Japan, Korea, Taiwan. Well, I find some countries missing. And we'd like to collaborate with scientists in Thailand, in Kagura. Okay, let me briefly discuss about the Kagura experiment. It is a very large laser interferometer experiment. It has 3-kilometer arms. And in particular, this is located underground to minimize the seismic noise. Also, we have another interesting features to use cryogenic mirrors. And here, I just want to show you briefly about our laser interferometer. We have the 3-kilometer vacuum tube, of course. Then the middle photo shows the central area. All of them are actually inside the clean booth. Therefore, you cannot see very well. But anyway, the instrument is extremely complicated. And in addition, we are going to use the cryogenic mirror made of sapphire. It is 23 kilogram sapphire mirror. As I said, Kagura is an international collaboration based largely on Asian countries and regions. We work together for the Kagura project and for the gravitational wave astronomy. By the way, this photo is a little bit old. This photo was taken in 2019 before the COVID-19 pandemic. We are coming back to the full face-to-face meeting, essentially. And actually, during the pandemic, we realized the importance of the face-to-face meeting, face-to-face discussion. This is really important for the communication of various people from various countries and regions. By the way, you may wondered why Kagura is mostly the Asian collaboration. In fact, there are 3 large gravitational wave projects going on, one in United States, another in Europe, and the third one is the Kagura project. Now, the scientific output will be maximized by the global network. For example, the pointing accuracy of the gravitational wave event will be much improved by combined analysis of all the data. Therefore, Kagura joined the network observation with LIGO and Virgo, United States and Europe. So, we are working together globally. So, all these projects are working together. And certainly, 3 projects have to understood each other, and this is very important. And well, I'm almost finishing my talk, but before finishing, I just want to mention one thing. This is the statement issued by the International Union of Pure and Applied Physics, issued on March 1st, 2022. Of course, this was a statement on the occasion of the Russian invasion to Ukraine. Of course, we were really worried about this. However, in this talk, I'd like to concentrate on the later half of this statement. Let me read. In our 100th anniversary this year, we note the critically important historical role that IUPAC has always strived to play in bringing physicists together across political divides, even during our most difficult years in the past. IUPAC continues to embrace and promote scientific collaboration across the world as a driver for peace. So, we believe scientific collaborations are playing a really important role for peace building. Okay, let me summarize. Neutrinos and gravitational waves are exciting scientific fields. However, to produce significant results, we need large and complex detectors. To construct and operate these detectors and to analyze the data from these detectors, we have been forming large international collaborations. We work together for science. In my opinion, science is more important than the political divides. I think that science, in particular the international scientific collaborations, plays a very important role for peace building. And finally, I want to mention that I hope that many of you, young people, become scientists to contribute to the scientific development and to the peace building. And I also hope that Thai and Japanese scientists work together much closely in scientific collaborations. Okay, that's all from me. Thank you very much for your kind attention.
Thank you, ladies and gentlemen. Please join me in giving our esteemed keynote speaker a big round of applause again. We shall now have our second talk by Dr. Chayanit Asawatthangtarakundi from the Department of Physics, Faculty of Science, Chulalongkorn University, who has her profound interest in experimental particle physics. She has broadened her research interest to include neutrino physics and has become a member of the Scattering and Neutrino Detector at CERN. She is also active in education and outreach program in the IceCube collaboration, which operates a neutrino detector at the South Pole, supported by the IT Foundation of Her Royal Highness Princess Mahachakri Sirinthorn. Ladies and gentlemen, please welcome Dr. Chayanit Asawatthangtarakundi.
Ladies and gentlemen, good afternoon. My name is Chayanit Asawatthangtarakundi, a faculty member from Department of Physics, Faculty of Science, Chulalongkorn University. And I am a particle physicist who has been working with the compact muon solenoid or CMS collaboration at CERN. I am also a co-chair of the implementation team on diversity and inclusion for the CMS collaboration. It is my great honor today to have the opportunity giving this talk after Professor Takaaki Kajita in the context of diversity and inclusion in science, collaboration, and a bridge to peace. So my talk today will focus on the role of diversity and inclusion in scientific collaboration. As a member of CMS collaboration, one of the largest and the most diverse collaboration in the world, I would like to share my own experience on how diversity and inclusion could contribute to build a bridge to peace. First of all, what comes in mind when you hear the word of diversity? Is it the gender? Diversity is not just refers to about the gender balance, but it refers to categories in which group of peoples can be differentiated. For example, different age, nationality, educational background, perspectives, physical appearance. As you can see, I listed here on the slide. And valuing diversity in the workplace is about recognizing and leveraging people's differences. This is not a new concept. It has begun since 1960s. Usually when we talk about diversity, it always comes together with another two words, equity and inclusion. Equity generally refers to a fair treatment, or simply speaking, it focuses on the way people are treated and the way resources and opportunities are equally distributed. Inclusion or inclusivity means how to create the working environment where everyone feels welcomed, respected, and value to fully participate. Or in another word, diversity, equity, and inclusion is the concept about making everyone work together and stay together in peace. And with this concept in mind, now let's have a closer look at the importance of diversity, equity, and inclusion in scientific collaboration. If we think about it, diversity in science is fundamental for driving innovation and comprehensive understanding. Because when we bring together people from various backgrounds, cultures, educations, or geographic, we open doors to multitude of perspectives. This is not just about seeing things differently, but it's about solving problems in the way we might have never considered before. And moreover, diverse teams can address a wider range of scientific questions and challenges, leading to a more inclusive and broader impact to scientific outcomes. For example, scientists from different countries or multidisciplinary might approach to one problem differently and get to new methods and innovative solutions. In fact, there are many studies have shown that diverse teams are more creative and innovative. And I would like to share my own experience from the CMS collaboration and strategies that the CMS collaboration initiates to encourage everyone about diversity and inclusion. But first, let me introduce what CMS is. The CMS collaboration or CMS experiment, as you can see from the picture, this is one of the most complex particle detectors in the world. It sits at one of the 4 collision points of the Large Hadron Collider at CERN. It is designed to observe new physics phenomena from particle collisions that happen at the LHC. The mission of CERN and CMS experiment include finding the answers of the universe, advancing the frontiers of technology, training the scientists of tomorrow, and bringing nations together through science. One of the most important scientific outcomes by the CMS collaboration is the discovery of the Higgs boson in 2012, which later on awarded the Nobel Prize to Professor François Englert on the left-hand side and Professor Peter Higgs, in the right-hand side in 2013. And as you can see that to build such a complex particle detector and to reach our scientific goals, we need a lot of person powers to accomplish this. There are about 6,000 members in the CMS collaboration, including particle physicists, engineers, and technicians from 247 institutes in 57 countries around the world. One could say that CMS is one of the largest international scientific collaboration in history. And in order to make our CMS collaboration is a better place for everyone, CMS had set the rules or the code of conduct regarding diversity and inclusion. And let me just read through some of them. It is everyone's responsibility to maintain professional environment in an atmosphere of tolerance and mutual respect. It is everyone's responsibility to abstain from all forms of harassment, bullying, and mistreatment of any kind. It is also everyone's responsibility to keep in mind that behavior and language deemed acceptable to one person may not be to another. And since 2017, CMS collaboration has founded a so-called the CMS Diversity and Inclusion Office to help foster a working environment in which all members feels welcome, respected, and can contribute to their greatest potential. Here you can see from the data collected by the CMS Diversity and Inclusion Office, the members of the CMS collaboration are diverse in terms of age, gender, professions, regions, and nationalities. So it is essential to encourage everyone to realize the importance of diversity and inclusion. However, several challenges can arise when attempting to integrate these concepts into such a large scientific collaboration. For example, language and cultural barriers. When the team members speak different languages or come from different backgrounds, it can be easily lead to misunderstandings and sometimes even slow down the progress to reach the important scientific goals. Resource allocation is also another challenge. Usually resources are not distributed equally, which can disadvantage certain groups and limiting their ability to contribute effectively to scientific efforts. Discrimination refers to the way funding is allocated or how research opportunities are offered. Unconscious bias could affect decision-making processes. It can influence who is selected for the teams, whose opinions are valued, and whose contributions are recognized. There could be also challenges from underrepresented minorities, accessibility, and time zone to schedule the meetings for members in different continents. So, acknowledging these challenges is the first step towards building a bridge to peace through science. And here, let me show you. Here is how the CMS collaboration enhanced the diversity and inclusion in our collaboration. Apart from the code of conduct, CMS collaboration has initiated various diversity and inclusion programs and policies. One example is a so-called implementation task force on diversity and inclusion report, which I am also one of the co-chairs. This report is the implementation plans for diversity and inclusion recommendations for the CMS collaboration. It is aimed to improve, monitor, and grow the diversity inclusion efforts. Here I just listed a few examples of what we have implemented in this report. First, collect diversity, equity, inclusion information in the CMS database. In this report, we recommended that information on diversity and inclusion shall be systematically collected and monitored, and at least once per year, analyzed and presented to the collaboration. Concerning the management selection procedures, we recommend appropriate procedures and criteria shall be defined on nominations and selections of candidates for management positions. This should be well documented and kept on record. Training and mentoring programs. We recommend that the training and mentoring shall be made available to all CMS members and managers in all aspects for successfully carrying out their positions in the collaboration. And last, it's about lessons learned since the COVID-19 pandemic. CMS collaboration shall take advantage of new technologies during the COVID-19 pandemic to facilitate worldwide collaboration. In particular, we should explore and find better ways to collaborate and include many remote members who until now still have limited access to participate, such as optimizing the way to organize the virtual and hybrid meetings. And now just bring me to the summary. To bring all nations together in large scientific collaboration, we need to respect everyone who have different perspectives, cultures, backgrounds. This picture on the left side shows the members who have made significant contributions to the CMS collaboration and selected to the CMS Award last year. CMS collaboration awards people who work in the collaboration every single year. These awards are not only related to research, but also include recognitions for people with talents in various fields. For example, software and computing, hardware development, social media engagement, or even photographing and designing and outreach. This award is aimed to encourage everyone to understand that every role is important in the collaboration and to feel welcome to contribute to their greatest potential. It creates a great workplace and healthy environment within the CMS collaboration, acting as a bridge to peace. Another picture shows that the overall CMS publication in the past 13 years, since the first data taking in 2010. It provides a kind of proof of concept regarding the impact of diversity and inclusion in the scientific collaboration. There has been a significant growth of the performance. In various aspects, this is not only the one for physics, but we also have the one from detector performance, like hardware. As said, when everyone realizes about diversity and inclusion, it leads to a wider creativity and problem-solving solutions, because everyone feels comfortable to express themselves and bring out their best performance to the collaboration. Finally, I would like to thank Chulalongkorn University, in particular, the President, Professor Bandit Ua Aporn, the Dean of Faculty of Science, Professor Pranat Pothiyarat, the Head of Department of Physics, Assistant Professor Sochipong Chatraporn, and including our management teams, colleagues, and our staff teams, who always support diversity and inclusion and make Chulalongkorn University one of the greatest workplaces in Thailand. Thank you very much.
And now, as a follow-up to the special talks we have heard, we will have a Q&A session with questions from the audience submitted by QR code. To facilitate the Q&A session, I would like to invite Associate Professor Dr. Surachet Limkamnert from the Department of Physics, Faculty of Science, to be an MC for the Q&A sessions. He was chosen as one of the Thai representatives for the 60 Lindau Nobel Laureate meeting in Germany. He has a lot of experiences working as a commentator in the science-related TV game shows such as Vitaya Saprayut and Vitsuvit, which are dedicated to promoting science awareness and education in Thailand. Ladies and gentlemen, please welcome Dr. Surachet to take over the stage.
Thank you very much. It's truly an honor to be here today, having just listened to a very insightful talk from Professor Kajita and on the importance of science for peace building, and gaining a deeper understanding from Dr. Shanit on the pivotal role of diversity as a bridge to peace. Now let's continue this enriching dialogue. I'm sure many of us in the audience would like to ask lots of burning questions to our two speakers. Now, without further delay, I'd like to invite Professor Kajita and Dr. Shanit back on stage for engaging in an insightful conversation. Please welcome back. Now I have lots and lots of questions from all of you from my phone over here. So if you see me playing with the phone, I'm not playing with the phone, okay? just to make sure because my boss is here and my boss's bosses are here. Okay, so let's get started with the first question. This one is from Kun Apishat from Private Self, I think Private Self Organization. His first question is, how could you as a scientist help world peacemaking?
So, first
For you, Professor.
Thank you. Well, certainly, first of all, we are not the political people. Therefore, we are not directly working for the peace building. However, as I discussed today, we are collaborating internationally with many people from different cultures, different nations. And I think so far we have been very successful, and we think this will contribute to some extent to the peace building.
Okay, I think this is as a follow-up question. As a scientist who's also involved in the admin side of things, how do you think we can use science and governance together to make the world a more peaceful place? I know you have to do lots of the admin stuff, right? And then to build such huge projects, and two of them.
Well, first of all, in a scientific collaboration, well, certainly, if we are not happy, if all the people are not happy, then the collaboration will not work well. So it's very important that we make the atmosphere that they can work together happily. So this is really an important thing.
Okay. Next one for Dr. Shianit. In your experience, how has diversity in scientific collaborations led to creative problem solving and more robust research outcome? Do you have any specific examples that stand out to you?
Thank you for the question. So I think let me take the COVID-19 pandemic as an example, because if you imagine that we are working in the very large collaboration when the pandemic arises, everyone kind of struggle how to work in the next step. But because we are in the diverse teams and everyone trying to find a solution to improve things, right? And this comes up with, as I show in my slide, the implementation task force on diversity and inclusion. We're trying to think the solution how we can organize the meeting for different people from different continents. And this, you can also see in my last slide that even during the pandemic, our performance still get growing and didn't stop from the pandemic. I think this one is one of the examples.
Oh, I see. Thank you. Now back to you, Professor. This question is from Kun Supawit Puttisuwan from Mahasakam University. What is the most challenging obstacle in peace building, and what would you suggest for the solution? This is a tough question.
Well, okay. Well, related to the previous question, certainly we have difficulties during the pandemic. The real communication was not possible. And certainly this was one, well, in a sense, a challenge for the peace building. We really have to talk to each other, meet each other. That is really important. That is what we learned, one of the things we learned during the pandemic.
Okay. And one more question from Kun Supawit. Since I am just a student, I don't know what to do or what can I do in my part of peace building. However, I want to do something. What would you suggest?
Well, okay. I would like to suggest this way. Well, certainly you have things that you'd like to do in your life. And if you work hard with your colleagues in the international community, that will contribute to the peace building.
Okay, thank you. Now, for Ajahn Chayanit, facing challenges like language barriers and cultural differences is significant. Can you highlight practical strategies, perhaps from CMS or elsewhere, that effectively enhance diversity and inclusivity, creating an environment where everyone can contribute at their best?
Okay. Yes, as I mentioned about the pandemic, so we develop all kind of like optimize the way people organize the meeting is one way, and then to compensate or to work out for the challenges on culture and languages barriers, we like during the meeting, for example on Zoom, we enable the closed captioning feature that people who's not using English as the first language can follow the meeting. We also provide the recordings with the closed caption. This is one thing. And then in order to close or to fill the gap between language and culture, we also try to, so CMS has encouraged people to get into the management positions from different cultures, different backgrounds. So these people understand, and then they can fill the gap as close as much as possible.
Okay,
Yes.
thank you. Okay, we have one more question from the audience. Back to you, Professor. What is your next study after proving the subatomic particle has mass?
Oh, thank you. Well, as I discussed today, I'm now working on gravitational wave. However, well, in our project, we have not observed gravitational waves yet. Therefore, the next target is to really observe gravitational waves in our detector. And we'd like to contribute significantly to the gravitational wave astronomy.
I see. And are you interested in taking Khun Apichat as your next student? The guy who's asking the question. Are you still accepting students to work for you?
Oh, thank you. Very unfortunately,
It's too bad. It's too bad.
well, I have the first retirement at the end of March next year, and after that, I cannot supervise students.
It's too bad, Khun Apichat, wherever you are.
I'm sorry.
Okay, but you still continue doing your research?
That's
work?
right.
Okay. That's kind of like selective retirement, right? You pick which part you don't want to do, and then you call that the retirement. You can still enjoy the research and keep doing it. Okay. Now we have a technical question, this one, from Ajahn Titi. The distance of 3 kilometers is very long for vacuum environment. What is the ideal distance for mirror to be able to pick up the signal?
Ideal distance of the mirrors.
The mirror.
Well, longer is better.
Longer is better. Okay.
Yeah.
Does that satisfy you? Okay. Okay. Now, back to you, Ajahn Chayanit. You mentioned the compact muon solenoid collaboration at CERN. Could you share some notable diversity, equality, and inclusion activities within CMS that contributed to important scientific discoveries? I should give you like a longer time to think, right?
Yes, so the diversity and inclusion activities, okay, let me put it this way. So
like frisbee every
yeah.
like, other week or something.
Okay. So to work in this large scientific collaboration, it's not just only one particle physicist. It also includes engineers, like technicians, and everyone. So in the CMS collaboration, we try to encourage to organize the mentoring and training programs. This I also put like these strategies on my slides, but I can explain a little bit more. So we organize the mentoring programs for newcomers like students, young researchers, when they start their role in the experiment in the CMS collaboration, so they don't get lost. And even the training for managers, when they get into the new position, they also like can fully start their new position. I think this is the example of the diversity and inclusion activities that this to bring together that everyone knows their roles and make a scientific goals, that outcomes. Yes.
Okay, thank you. Now, the questions keep on coming. Now, when the new question comes, my screen will just move up a little, so I have to scroll back down. This one is for you, Professor. Another technical question. I think this one is easier than the last one. Would there still be any effect of seismic noise in the Kagra project, or it will be 100% null?
Oh, thank you. This is, in fact, this technical question is very important.
Okay.
Well, in fact, even in underground, there are still seismic noises, which is many orders of magnitude larger than the expected length change due to gravitational waves. Therefore, we have a very advanced seismic attenuation system, but this is a rather complicated system. We have still many technical problems, so we have to improve the systems further. So this is one of our challenges.
Okay, thank you. Now, I have this question which I can ask you both. Let me start with you, Dr. Shayanit. How do you explain to common people about the importance of cosmology and astronomy? I'm sure lots and lots of your friends might ask you similar questions.
Sorry?
How to explain to people the importance of cosmology and astronomy? What do you, well, did your mom ever ask you this question?
Yes, okay. So usually when my friends or my close people ask me about this question, I will just let them imagine that we would like to know where we come from, or what is the origin of the universe. That's why we would like to understand the cosmology and astronomy. And then they ask me back, and why you want to know? This is because, if we understand since the origin of the universe, and then I think we can apply the knowledge in various aspects, right? Including the technologies that we developed to build the complex experiment, also help to improve our world, in various aspects. That's
Thank you.
My answer. Thank you.
What about you, Professor? You
Yeah,
have to spend lots and lots of your time under the tunnel, 1 kilometer down underneath the earth, right?
Yeah.
You have to.
Well, okay, thank you. Well, basically my answer is quite similar. In the universe, there are still many unknowns. Well, for example, some time ago, people thought that they understood the basic components of the universe. However, now we know what we know is only 5% of them. about 70%, 75% are so-called dark energy. Well, of course, we have named, but we have no idea what are they. Another 20% is called dark matter. Of course, we know dark matter exists, but we do not know what are they. So there are many, many unknowns in the universe. Therefore, as scientists, we should try to understand them.
Thank you. I think those are good enough examples, like to tell people, and they would follow you to spend their time under the cave also. Just kidding, sorry. Okay, now we have a question regarding the Japanese government in promotion of science. Could you please describe how Japanese government promote, support, subsidize mid to large-scale scientific experiment programs? This is from Kun Keng.
Well, thank you very much. We have, in fact, a special program to support large-scale pure science projects. And in fact, by this program, for example, Super Kamiokande and Kagura are supported. That is okay. That is the okay part. The problem is, the Japanese government science budget is essentially constant. Okay. But on the other hand, the science projects is getting bigger and getting more complex. And that means people need more money, but unfortunately, the Japanese budget does not allow us to think too much about the future large scientific projects.
Okay, thank you. Now, next question for Ajahn Chanyanit. Sex and genders are so diverse. How can science collaboration cope with it?
Okay, thank you for the question. I think this one is also a good question. In large collaboration, I think it also in every places, in many places right now, we're trying to so people have a chance to not specify their gender, right? So this is because gender has nothing to do with their performance and their ability. That's why, like, when I talk about gender on my slides, that CMS collaboration also collect the data about the gender. We just get this record from the database, and we don't really care about like what gender you are or what sexual you are, like in terms of performance.
Okay, thank you. We have one question for Professor Kajita. What kind of personal challenges have you faced in collaborative projects so far, and how did you overcome them?
Well, thank you. Well, about 22 years ago, Super Kamiokande had a large accident.
I see.
In about a minute, we lost more than half of the detectors.
Whoa.
Photo detectors.
Okay.
Yeah, that was really a very serious accident. But, well, I think at that time, we were lucky. First of all, we had a very strong leader. Essentially, he decided within a day to build the detector and started talking with many people. Also, he announced to the world community that Super Kamiokande is going to be rebuilt. Well, of course, there was no well, of course, no one was sure if we were able to rebuild, but he already mentioned. So this way, this kind of strong mind was very important, and because of this strong mind, and also by the support of the Japanese government, Japanese people, we were able to rebuild the detector, and we started the experiment.
That's very nice. Thank you. My mom lost her mind after losing just one bulb in the kitchen. That's something. Now we have questions from Chile from Shrewsbury Riverside. The first question is, how will the further investigation of neutrinos benefit society? Should we keep doing neutrino research?
Well, thank you for this question. Well, it may take maybe 1,000 years to benefit the society directly. But we think it's very important to know about neutrinos, to know about the nature, to know about the universe as a humanity. Therefore, we'd like to continue the neutrino research.
Okay.
Do you mind if I add a little bit more answer?
Okay.
So this is to the student that asked the question. So if you think about like electrons, that we know electrons quite long time ago, right? But like only 100 years after that we discover electrons, we can use them for electricity. And now if you think about neutrinos, we just discover that neutrino has mass. And then we don't know, like we don't know how long that we're gonna use it for society.
Okay, thank you. The next question from Chile is that how would you get to be able to study particles in Camille Kandi? I think she would like to join your group.
Thank you very much. This is a bit too technical to talk about.
It's not straightforward. It's not just like applying after the talk and then you would get to go to Japan. Okay. So do you have like a minimum requirement? Does she need to first get into university and study physics for a few years and then start applying?
Yeah, that's right. Okay, well, the minimum requirement is we only accept graduate course students, not the undergraduate.
Okay, so I guess 5 more years for you. And okay. Okay. From SIBO, do the members of an international scientific organization always work together well? What do you do when there are disagreements?
Good question. Yeah, well, of course, we are scientists, and therefore, even if we have some disagreement, we continue to discuss. And typically, finally, we get a conclusion.
Okay. And he also would like to know if you like Thai food.
Huh?
Same guy. Professor
do you
Takaaki,
like Thai food?
do you like Thai food?
Oh, Thai food.
Yes,
Yes.
Thai
Oh,
food.
yes, very much. Thank you very much. I'm enjoying.
We just had a really good lunch just 2 hours ago. Okay. Now, back to a more serious note for Dr. Shayanit. Your talk emphasizes science as a bridge to peace. Can you provide insights into specific projects where diverse scientific collaboration promoted cross-cultural understanding and play a role in global cooperation for peace building?
Thank you for the question. So as I think I have already mentioned in my talk that I am one of the co-chairs of the implementation task force on diversity and inclusion at the CMS collaboration. And this task force just try to promote the diversity and inclusion projects and also try to improve like our collaboration working environment. This one can be one example.
Okay, thank you. And now back to you, Professor. And this one is from Jane. Understanding astronomy, would it help you to understand how our system, how our solar system is going to end?
End of our solar system.
That's right.
I think so.
Okay.
Yeah. Well,
Should we worry that will happen in a few years? Or?
no, don't
Okay.
worry. maybe, well, say, several billion years later, maybe you have to worry.
Okay, that's good to hear. Okay, all right. So studying Kamiokande project, is that for physicists? Can people with different backgrounds other than physics join Kamiokande project?
Of course, yes. Even if he or she has no weak physics background, he or she can essentially join the Super Kamiokande project. However, of course, we are talking about physics. Therefore, he or she should study physics.
Okay, that's preferable, I guess. This one is also about funding. Have you gotten some financial support from private sector?
Myself?
Yes.
Essentially, no. Well, we accept the donations from various people. But, well, unfortunately, in Japan, we do not have the culture of donation. So the amount we can receive is really limited.
I see. In Thailand, there's something called tax deductible. But even that, we don't get several support from private sector just yet, even though they can deduce the tax if they pay for some of the research. What about you, Ajahn Chayan? What funding do you get the money from the most?
So to work in the CMS collaboration, we got the funding from, first of all, Chulalongkorn University, from C2F, and also from PMUB. This is the outsource that we get outside the university. Mm-hmm. And thank you. Thank you for all the support.
Okay, question from Kun Supavit. Are scientists free from politics? Can they express their stances or beliefs? For example, campaigning for no war, global warming, or climate crisis? I guess both of you can answer, starting with you, Professor.
Well, thank you. In fact, I think in order to really overcome the global warming, scientists should be deeply involved. Well, certainly, we know the way to reduce the, CO2, but well, in order to really come to the zero carbon society, we still need various science. So I think we have to be very serious. Scientists have to be very serious about the global warming problem.
Okay.
Yes, my answer will be quite similar to Professor Kajita. So, like, I think as a scientist, we cannot just do the research work. We also have to concern about our global warming problems, and including this zero carbon issue. And I think, like, right now, I think every places in the world start to encourage these global warming issues and like the zero footprint, carbon footprint.
Thank you. Now we have a question from Kun Thanapon. Do you think there is the end of science discovery or research, or we have to find answers to something forever? Wow.
Okay, yeah, thank you.
We have only 1 billion years, if you remember.
I think, I'm afraid we have to continue research, and this will continue forever.
It doesn't look like it's going to end very soon. No.
Okay, I think this is not just about finding the answers, but when we have to admit that when we do something, right? When we research something, it always comes with new technologies, and that can help improve our world. And I think this should not stop, right? So this should continue.
Okay, thank you. The next one is for the both of you. Have you ever been exhausted studying physics?
No.
Okay.
Well, actually, to tell the truth, I want to study more. I have no time to study physics now.
Okay, for me, yes, sometimes. But because I think physics is my passion, so when you do the things that you're passionate with, then I think it's not gonna you will never feel exhausted from what you do. Yes.
Thank you. Back to a more technical question from Jane from Shrewsbury. Can scintillators be used to detect neutrinos? And does the Kamiokande use scintillators? And how is the photoelectric effect used?
Well, thank you for this question. Yes, scintillator is a very important tool for neutrino physics. In particular, the liquid scintillators are very useful. And, well, in fact, originally we worked in the Kamiokande experiment. That is the experiment previous to the super Kamiokande. Then, after finishing the Kamiokande experiment, the detector was converted to the liquid scintillator detector. And I was not involved there, but well, this experiment had a very significant result. So liquid scintillator is a very important tool for neutrino physics.
Thank you. Now we have a question from Kun Tawiwat from Physics Department. Amidst the ongoing global conflicts, how do you propose we engage with scientists from affected countries like Russia and Ukraine? I guess that's your question.
Sorry, could you say again?
How do you propose we engage with scientists from Russia and Ukraine?
Well, okay.
During the conflict, I guess.
Thank you, yeah.
Yeah.
Well, I introduced the statement of the International Union of Pure and Applied Physics. And certainly, at that time, we were very much worried about the Russian invasion to Ukraine. And I really hope this war will finish as soon as possible. And it is really our hope that we can work together globally for the development of science. And well, certainly, I hope we have larger voices from scientists.
Okay, let's hope so too. We have more questions from Mahasarakham University. Now that Japan is facing aging society problem, do you have younger generation manpower problem? If so, how would you solve that? If not, how have you or the government encouraged the younger ones to go into science?
Thank you. Well, this is really a very important issue in Japan. Well, first of all, I personally do not have a proposed solution to this problem, but I strongly feel that science is again very important to attack this issue, and therefore I would like to say to the young people in Japan that many of them become scientists.
Okay, thank you. I guess we have the time for just one question for each of you, starting with Dr. Shayanit. Drawing from your experiences, what are some key lessons or tips for other scientific communities aiming to enhance diversity and create an environment that nurtures the potential of all members?
Okay, thank you for the question. So I think different scientific communities have different structure of organization. So I cannot just simply take the CMS collaboration and share to and say that everyone can use the same method of CMS collaboration. But I think like the rule of thumb is that for other scientific communities, that if you want to accomplish the goal, then we should truly see what the problems are, and everyone should try to help solving the problems together in the context of diversity and inclusion, as I mentioned. Thank you.
Thank you very much. Now, for you, as a Nobel laureate, what message would you like to convey to the global community about the importance of science in fostering peace?
Okay, thank you. Well, in order to foster the peace, I think it's really important that many people from many countries, many regions, many cultures talk to each other. And science collaboration is one of the tools to foster this way. Therefore, I think science is very important.
And thank you very much. And that concludes the Q&A session for this afternoon. I want to extend my deepest gratitude to Professor Kajita and Dr. Chayanit for sharing your invaluable insights. It's been a real journey into the wonders of science and cooperation. And let's keep building bridges, celebrating diversity, and looking towards a future where science brings us closer together. Thank you. And may I return the stage back to you, Ajahn Sirintra.
Thank you, Ajahn Surachet. Okay, we might take some time to waiting for the stage setting. Okay. And now may I invite the Dean of the Faculty of Science, Chulalongkorn University, Professor Dr. Pranat Pothiyarat, to present the closing remarks.
Dear all, as we conclude this remarkable event, I'm filled with a profound sense of appreciation. Today we have had the extraordinary privilege of hearing from two experts, a Nobel laureate whose groundbreaking contributions have reshaped our understanding of the universe, and our young and rising star researcher whose innovative work promised to lead us into new frontiers of knowledge. First of all, I would like to thank you also our moderator, Ajahn Sirintra Sirisap, and Associate Professor Dr. Surachet Limkamner. You give us very interactive and delightful afternoon. Thank you very much. Professor Kajita, your achievements are a testament of a lifetime of dedication and intellectual. Your work has not only advanced our scientific knowledge, but also served as a beacon of inspiration for generations of scientists. Dr. Chayanit, your presentation today has been a clear indicator of our bright future. Your fresh perspective, innovative approaches, and relentless curiosity are exactly what the scientific community needs as we tackle the challenges of the changing world. To all the students, researchers, and enthusiasts here today, let this event serve as a reminder that science is an ever-evolving journey. As we depart, let us carry with us the inspiration and knowledge we have gained today. May we continue to nurture the curiosity that drives us, the courage to venture into the unknown, and the commitment to pursue truth and understanding. So on behalf of everyone here, I extend our deepest gratitude to both the speakers for sharing their invaluable insights and experience with us. Your contributions, both established and emerging, continue to inspire and challenge us. Thank you once again for a truly enlightening and inspiring event. We look forward to the ongoing contributions you both will undoubtedly make the world of physics and to the greater scientific communities. Thank you and safe travel to all. Thank you very much.
And now may I invite Professor Kajita, our keynote speaker, to receive a token of appreciation on the stage, please. And also Dr. Shianit to receive a certificate of honor. Thank you. Ladies and gentlemen, this marks the end of today's activities. Thank you very much for your keen interest and participation this afternoon. We look forward to welcoming you to the subsequent talk in the Bridges Nobel Laureate Talk series, which you can find at the OIA website at www.inter.chula.ac.th. And once again, please don't forget to complete our post-event survey as well. Thank you very much. ขอบคุณค่ะ